Alrighty, let's say we have a reaction we're interested in, and we can measure the concentrations of all the reactants and products at equilibrium, which is possible to do for sure, depending on the reaction you're looking at and how much you know about the different molecules involved. It is not unreasonable at all to be able to measure the concentrations of everything as the reaction progresses. So if we want to take that information and find the equilibrium constant, it's a pretty straightforward process. It's actually not that difficult, as long as we actually know the reaction that's taking place. So if we know, for example, the reaction we're interested in is this one, hydrogen gas and iodine gas coming together to form hydroiodic acid, and we know the equilibrium concentrations, all we have to do to find the equilibrium constant is just take those concentrations, plug them straight into the constant, and solve for the numerical value. And as you can see here, no matter where we start with our initial concentrations, and no matter what equilibrium concentrations we end up at, the equilibrium constant is still going to end up being 50. So whether we start with only reactants, only product, the same amount of reactants and products, differing amounts of reactants, no matter what it is, as long as we have at least all of the reactants or all of the products, we will always end up at equilibrium. And no matter what the concentrations are at equilibrium, when you plug the concentrations into the equilibrium constant expression, it will always give you the same number, which is 50 in this case, for this particular reaction at 445 degrees C, which is really, really hot. You will have an equilibrium constant of 50. Now, that is well and good. Like, if you are able to do that, more power to you. But what if we can't measure everything? What if we aren't able to measure the concentration of every molecule that is reacting in the mixture? Are we doomed to failure? Doomed to wander the chemistry wasteland, wondering, oh my, I'm just wondering all my life, what is this equilibrium constant? No, we are not doomed. In fact, if we know the reaction that's taking place, all we have to know is one of the molecules that is involved. All we have to be able to track, I should say. All we need to be able to monitor the concentration of is one of the molecules involved. Because if we know the reaction that's happening, and we know what's happening to one of the molecules that's involved, we can use our good friend from Gen Chem 1, stoichiometry, to figure out the rest. We're going to do this using a handy little tool that we call an ICE table. Some people call it a RICE table. But either way, what this table is going to allow us to do is tabulate our known values in terms of initial concentrations and equilibrium concentrations, and figure out how things are changing, and then use our balanced chemical equation to work out, okay, if we know how this one changed, that means that this other reactant must have changed in this way. So we're going to do this quite a bit, actually, both in this chapter and in the next two chapters. ICE tables are going to be very, very handy for us. So I have a few little bullet points here talking about how we're going to go through this process, but I think it might actually be easier to just go ahead and jump into an example here and show you what I'm talking about, rather than describing it. So we have a closed system that initially contains a millimolar of H2, 2 millimolar I2, and it is at 448 degrees C. This is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of hydroiodic acid is 1.87 times 10 to the negative 3, and it asks us to calculate Kc at 448 degrees C for this reaction. All right, now this is actually going to be worked out for us in the slides here, so we're not going to be writing out and doing a lot of stuff here, but it is going to be worked out step by step. So when we're writing out these ice tables, they're going to be laid out like this, where we have our initial, change, and equilibrium. That's where we get the ice from. And by the way, the people that call it a rice table, it's because they put the reaction here. So they have the reaction, initial, change, equilibrium. I don't really care which one you call it. But anyway, so we're going to put down what we know, what we started with. So in the question, it told us what these two started as, what their concentrations were, and it told us what HI finished, what its final concentration was. Now, we didn't actually, we weren't told what the initial concentration of HI is. As a general rule, though, for any of the questions we're going to look at, if you are not given the concentration of a product, you are safe to assume that you have none of it. So I'll say that again. So if you are not given the concentration of a product in a problem, you are perfectly safe to assume that you have none of that product. It would be up to the person writing the problem to tell you if you had some of it. So because we weren't told anything about the concentration of HI, we just assume that there is zero of it in the mixture. Now, in order to find Kc, we need all three of these equilibrium concentrations. Because remember, Kc is the concentration of the products over the concentration of the reactants raised to their powers. So we need all of those concentrations, and we only have one. We do have the one, and that's a good start, but we need the other two. And so what we're going to do is we're going to use stoichiometry to work out those other two. And we're going to do that by thinking about what we know. So we know, for example, that we started with none of this, but then we ended with 1.87 times 10 to the negative 3, and this is molar. Everything here is molar. What that means is we increased our concentration for that particular product by 1.87 times 10 to the negative 3. That's the change that happened. It was at 0, it increased, that's how much it increased. We also know, based on the stoichiometry, that whatever, and actually let me go back here for a second, whatever the HI does, the I2 and the H2 are going to be related to that. They're going to change by 1/2 of whatever this does. And we know that from this balanced chemical equation. So the balanced chemical equation tells us that for every one of these and one of these that reacts, we get 2 of those. So whatever change happens with I2 and H2, we see 2 times that change in the HI. And again, that is purely based on the coefficients. So each of these have a 1 in front of it that is usually left out, and this one has a 2. And so because of that, we know that H2 and I2 decreased by half as much as the HI increased. So if you take 1.87 times 10 to the negative 3 divided by 2, you get 9.35 times 10 to the negative 4, and it's negative because these are reactants, they're getting used up. They're going away. So this increased, but these are going to decrease. So they're decreasing by half as much as the HI increased. So at this point, we know where they started, we know how much they changed, and so we can just apply the change to the initial concentration, and that will give us these equilibrium concentrations, and we can plug these directly into the equilibrium constant, not forgetting the coefficient here, and that gives us a value of 51. Now, those of you that have a good memory might realize, wait a second, this is 51. We just saw this reaction, and you told me that Kc was 50.5 or something like that. I think it was 50.5, or just 50. Like, what gives? Here it's 50, over there it's 51. Well, the temperature is different. Here it's 445. Here the temperature is 448. So Kc increases by a little bit as you increase the temperature there. So that's why it's a little bit different. But pretty close to the same. All right, so we'll call it there for this video. In the next one, we'll take a brief look at the reaction quotient, and it will be very brief because we've already been introduced to it in a previous video, and then move on to working through problems where we're not given any equilibrium concentrations. So you can look forward to that in the next video.